Recently, the most powerful solar storm in 2 decades hit Earth, creating spectacular displays of auroras, known as the Northern and Southern Lights. This event was triggered by a group of sunspots, 16 times the size of Earth, which released multiple X-class solar flares and coronal mass ejections directed at our planet. These solar emissions led to severe geomagnetic storms, classified at the highest intensity level, G5, making them the most intense since the 2003 Halloween storms. As a result, the Northern Lights were visible as far south as Florida and Mexico, while the Southern Lights were seen in New Zealand, Australia, Chile, and Argentina. These solar storms have had significant effects on technology, both in space and on Earth. Elon Musk mentioned that the Starlink satellite service was experiencing issues due to the storm. On the social platform X, he noted that the satellites were under a lot of pressure, but holding up so far. The storms also disrupted power grids, GPS systems, and high-frequency communications in some areas. These events suggest that the solar maximum, a period of peak solar activity in the sun's 11-year cycle, may arrive sooner than expected. As the sun's magnetic field flips, more geomagnetic storms are likely in the coming months. While these storms may create more beautiful auroras, they could also disrupt radio communications and electrical infrastructure further. The recent solar storm was caused by a sunspot group named AR3664. Sunspots are temporary dark areas on the sun's surface, appearing darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 3000 and 4500 Kelvin, compared to the surrounding area's temperature of about 5800 Kelvin. The AR3664 cluster rotated into Earth's view a few days ago and rapidly grew to 16 times the size of our planet, spanning 200,000 kilometers or 125,000 miles, becoming one of the largest sunspots of the current solar cycle. The Space Weather Prediction Center had warned of increased solar flare risk from AR3664 at the start of the month. AR3664 emitted 75 M-class flares and 10 X-class flares within a week, accounting for 50% of this year's X-class flares. A solar flare is a sudden, intense burst of radiation on the sun, resulting in a bright flash of light across various wavelengths. Solar flares can last from minutes to hours and release massive amounts of energy. The light from these flares reaches Earth in just over 8 minutes. They are categorized by strength, B class being the weakest, followed by C, M, and the strongest, X. Each category increases by a factor of 10, with subcategories from 1 to 9. While C-class flares are generally too weak to impact Earth significantly, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing risks to astronauts. Many people confuse solar flares with coronal mass ejections, CMEs. A coronal mass ejection is a large cloud of magnetized particles ejected into space from the sun, occurring when the sun's magnetic fields explosively realign. Coronal mass ejections can travel over 1 million miles per hour and may take up to 3 days to reach Earth. Unlike solar flares, which are bright flashes of light, CMEs are vast clouds of solar material. When a CME reaches Earth's magnetic field, it can create currents that drive particles toward the poles, resulting in auroras. Essentially, both phenomena stem from the sun's magnetic realignments, but differ in appearance, travel patterns, and effects on Earth. Solar activity increased on May 3rd with the detection of an X1.6 solar flare. Within the next 48 hours, 2 additional X-class flares were observed. The intensity rose further when the sunspot region emitted an X4.5 flare, releasing tremendous energy. The first CME was seen departing from the sun on May 6th. On May 8th, another CME followed an M8.6 flare. On May 9th, 2 more X-class flares produced 2 additional CMEs. By May 10th, 4 CMEs were heading toward Earth, with the last three merging into a larger event known as a cannibal CME, due to their differing speeds and overlapping paths. When a CME reaches Earth, the planet's magnetic field deflects the solar storm, creating a funnel where the gas streams down at the poles, leading to daytime auroras. The magnetic fields stretch and couple further back, breaking like a rubber band, allowing gas from the solar storm to stream along magnetic lines toward the poles on the night side, resulting in nighttime auroras. Auroras are typically thought of as green, but during intense solar activity, they can also display vivid red glows. The colors depend on the particles involved and the altitudes of these interactions. Blue and purple auroras occur when solar particles interact with molecular nitrogen at altitudes up to 100 kilometers, 62 miles. Green auroras result from interactions with oxygen at 100 to 300 kilometers, 62 to 186 miles. The rare red auroras happen when these interactions involve oxygen at higher altitudes, between 300 and 400 kilometers. For red auroras to be visible to the naked eye, they must be at least 10 times brighter than green ones. Geomagnetic storms can significantly impact our electrical grids and satellite systems. During such storms, geomagnetically induced currents, GICs, can flow through power lines and transformers, causing them to overheat and malfunction. This can lead to transformer failures, protective equipment tripping, overloaded transmission lines, and damaged generators. Severe cases can result in large-scale blackouts, such as the 1989 storm in Quebec, Canada, which left 6 million people without power for 9 hours. The 2003 Halloween storms caused widespread satellite and communication disruptions and power grid issues in Sweden. In 2022, a solar flare caused the loss of 40 newly launched Starlink satellites. Currently, the sunspot group AR3664 has moved behind the sun's disk, making it temporarily invisible from Earth. So its emissions won't affect our planet for the next 2 weeks. However, AR3664 is expected to reappear and face Earth again in 2 weeks. Based on previous observations, this sunspot group may remain active when it becomes visible again. Just before it moved out of view on May 11th, AR3664 produced significant solar activity, including an X1.8 and a larger X5.8 flare, the latter associated with a coronal mass ejection, CME. This suggests that AR3664's cycle of activity is not yet over and could produce more solar flares in the future. AR3664 is an exceptionally large sunspot, visible from Earth without magnification, though looking at the sun without proper protection, like a solar filter or eclipse glasses, is dangerous. Its size is comparable to the sunspot responsible for the Carrington event in 1859, the most intense geomagnetic storm on record. That storm caused sparking and fires in telegraph stations, and made auroras visible as far south as the Caribbean and Mexico. In 1859, the telegraph system was the most advanced technology. Today, our society heavily relies on satellites and other technologies that require stable magnetic conditions to function properly, making us more vulnerable to the effects of significant solar activity, such as that from sunspots like AR3664. The increased dependence on electricity and technology in modern society means that disruptions could lead to trillions of dollars in losses and pose significant risks to lives reliant on these systems. A Carrington-class event today could cause damages estimated between $0.6 to $2.6 trillion in the US alone. Recognizing the threat of extreme solar storms is crucial, and proactive measures are needed to protect our technology and infrastructure from potential devastation. The solar storms experienced in May 2024 indicate that the solar maximum, along with the flip in the sun's magnetic field, may occur sooner than previously anticipated. Thanks for watching.